this,
Who eats the method?
well, you'll get an opportunity to redeem yourselves on test 2. Yeah, exactly.
If we get a 15% higher grade on our final for our next midterm, will you cancel the other midterm?
No,
No?
but I do shift the weight of your lowest test to your final exam, assuming your final exam is better. Obviously, I'm not going to do it if your final exam is worse. So, but I do that.
Okay.
One of your tests.
One of our tests. Good.
Yeah. Well, now I erased it, but there was a note saying, try this for review. Try this on your own, and then we'll use it for review next day. But let me just, sorry, you can't see, but there, my menu options were all weird. Last day we were talking about, well, solving exponential equations, but also logarithms. Right? And so if you have to solve for something in the exponent, what you're going to do is you're going to isolate the exponential expression. So just get only the exponential function on its own. And then you take the logarithm of both sides. And we talked about, okay, it can be log base anything really, but my go-to is log base e or ln or ln, if you want to call it that. And then you use the exponent property to bring down the exponent. So the exponent property is if you have the log, that's a generic log of a to the power of x, that's the same as saying x times the log of a, right? Bring that power downstairs. Thank you, is what that exponent property says. And so that's the, I call it the moneymaker, because that's how we're going to shake out an x that's in the exponent, right? And then you use algebra, so just move things around until you've solved for x, and then you did it. Okay. It left you with some examples, but we'll use them for review. So as I'm sure you're aware, in chemistry, pH is a measure of the acidity or basicity. Basicity. I want to say basicity because it's basic, right? I don't know. Basicity? No, I don't think so. Of a liquid. So, well, the pH, I guess. The pH is related to the concentration of hydrogen ions, so H plus, I guess. And we have this equation where the pH is the negative log of the hydrogen ions. And so if a liquid has a concentration of 0.0001 moles per liter, I had to change, there was a typo. I think it used to say Lieber, but I'm pretty sure it's supposed to be liter. We're going to find the pH, and that's the first thing we're going to do. The hydrogen ions are measured in moles per liter, and we have the units moles per liter. And so that's the first thing we're going to check in on. Make sure you have the same units. Otherwise, you'd have to do some adjusting. Yeah. So we get the pH is the negative log base 10, right? If it doesn't indicate and it's written as log, it's log base 10 of 0.0001. We can solve this without a calculator, right? How? I'll do a little side without a calculator. Kind of tricky, but we can do it, right? You can have the log of 0.0001 to the -1, right? The reverse exponent property. This -1 is being multiplied, so I can bring it upstairs. So then, what do I have? It's really going to be 10 to the power of something equals 0.0001 to the -1. But this, okay, we will kind of need a calculator, but not the log function. Or this is the same as 1 over 0.0001. But that's going to be a big number. So, but too early to tell, as in too early in the morning. 1 divided by 0.0001. 10,000.
Yep, too early in the morning.
It was a good effort though. Whoops, too many zeros there. So 10 to the power of something equals 10,000. Let's see here. 10 to the power of, last day we said 10 to the power of 2 is 100. 10 to the power of 3 is 1,000. So I'm going to go for 10 to the power of 4 and see what happens. All right, so 10 to the power of 4 equals 10,000. We suspect pH is equal to 4 then. Right, just kind of checking your work, but also getting warmed up with these logs. Remembering the rules from last day. Of course, we can just check it with our calculator, that's allowed. So what if we do the negative log base 10 of 0.0001? I get 4, womp womp. I guess not really a womp womp. That's good news. But we already knew that. Okay. What if you have to work the other way? So what if we have to determine the hydrogen ion concentration of a liquid with a pH of 7? So now the pH is 7, and we want to solve for what's inside the log. So I'll do the general formula because I'm about to scroll. Log of H there. Try to scroll there. Okay, so now I'm forcing the pH, was it 7? Yeah. Forcing the pH to be 7. And I want to solve for what's inside the log. Now, just like exponential functions, you want to get the log on its own, right? Or, I mean, you could bring the negative inside, but I'm going to bring it over to the left-hand side instead. So I get -7 must be the log of the hydrogen ion concentration. Wait.
Making a juice.
Splashy. The negative log of H plus. So if I move that negative over, I get -7 is the log of the hydrogen ion concentration. How do I undo logs? Or can I get at the logs? I raise it to be in the exponent, right? This is log base 10. So a convenient base would be 10. Okay? Use base 10 in the exponent. So then we get 10 to the -7. we want a movie too. 10 to the negative 7 is 10 to the power of log of the hydrogen ion concentration. Kind of squeezing it in there. Now, the log properties say that, okay, if you have b to the log base b of x, those are just going to cancel out and you're left with x, what's in the exponent. Yeah. And so 10 to the negative 7, it's really important that we did it to both sides, right? Otherwise you lose this equality, right? They have to stay equal. And so as long as you're doing things to both sides, then they stay equal. Is the hydrogen ion concentration. 10 to the negative 7 is going to be very small. I get, well, 1 times 10 to the negative 7 because it gives me in scientific notation. That's not very helpful. 1 over a million, I think. 10 million. If I try not to, yeah, I'm getting 10 million. Or we can just leave it like that. So the hydrogen ion concentration is 1 over, it's very small, or 0.00012 1, 2, 3, 4, 5, 6, 7. Right, 10 to the negative 7 is the same as 1 times 10 to the negative 7. Nice. Okay. So we'll work more with log properties today, of course, and we'll introduce some more log properties in the next section. But before we do, we can convert between periodic and continuous growth rates. So we saw earlier, right, we can have that continuous growth rate, which uses E, right? A times E to the kx is how we find if we have a continuous growth rate, K, versus our usual one is A times 1 plus R, but we've been writing it as B just for simplicity, right? But it is 1 plus R, where R is the growth rate. And so we can convert between the two if we say that, okay, f of x, both of these are f of x. So what I can do is I can write this guy on the left-hand side and this guy on the right-hand side, and then match them up and see how they compare. What we're going to find is that 1 plus R takes the place of E to the K and vice versa. And so I have A times 1 plus R to the X, but it's also the same as A times E to the K times X. Right? If I put brackets around that, now it should be relatively obvious, right? Even if you go ahead and you divide both sides by A, the A goes away, and then you've got a power of X on both. So then we get 1 plus R is the same as E to the K. Okay. So if we have something like a population grows 10% each year, okay. Now the periodic growth rate is the percent growth each time period. So for us, we have each year. Okay. And we want to find the continuous growth rate, K. So here, find K. Okay. we could start here. Let's do that. You don't have to, you can jump straight into 1 plus r is e to the k, and we have r, and you can solve for k, right? But let's take it one step back. A times 1 plus r to the power of x is, maybe I'm regretting this. Nope, stick to your guns, Emily. A times e to the k times x, or to the power of x. Oops. I think I said times, but I meant power. For some reason, even though it's the good time change, it just rocks me. And I get sleepy even though we get more. I don't know. It doesn't make sense.
I'm like falling asleep at like 8:30. I can barely stay awake anymore. I'm like, I'm dying.
Definitely. Yeah. I'm always like, well, it used to be 9:30. That's fine. We can divide both sides by a, like I said, and cancel those a's. And then we have 1 plus r to the power of x is e to the k. And I've separated those out intentionally. If I take the xth root of both sides, then that's how I'm going to ditch that x, right? And so if I take the xth root, that's the same as 1 plus r to the power of x times 1 over x. And I have e to the k to the power of x times 1 over x. 1 over x times x makes 1. So that's how I'm left with. Maybe I should show here divided by a divided by a. There. Sneaky. That's going to cancel. And now I'm left with 1 plus r is e to the k. We were given that in that little blurb, but now we have it for keeps. Now we know why we have it. So we were given that r was 10%, so 0.1. So I have 1 plus 0.1 is e to the power of k. So 1.1 is e to the power of k. E is just a number, right? It's an irrational number, but it is a constant, right? And so E is 2.71828, blah, 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 blah. And we know you have an E button on your calculator, but that's not the problem. The problem is that we want to get at this k, which is in the exponent, right? And so to bring exponents downstairs, we need a log. I'm going to use log base E, not only because it's my favorite, but also because I have a base E here, and so then they'll cancel. So then I need to do it on both sides. The log of 1.10 is the log of e to the k. Log properties. Technically, what are you doing? You're using that log property and bringing that k out front. And then the log base e of e to the power of what makes e to the power of 1 makes e. And so log base e of e is 1. So I still have the natural log of 1.1 is k. And I'm not going to write the 1. Because that's the reason I used log base e, was to ditch it. And there you have it. K is the natural log of 1.1. This is the exact answer. Exact answer. Or K is roughly, let's see here. The natural log of 1.1, 0.0953101798. So roughly 9.53% continuously, right? We had 10% annually, 9.53% continuously. They should be relatively close, right? If you're growing continuously, then you don't need as fast of a rate as 10%, right? So there's lots of ways to check your answer, but to make sure it makes sense, or 9.53% continuously, right? Because 10% each year versus the continuous growth rate, 9.53, just slightly less, but still relatively close. I'm happy with that. Okay. Any questions? From last day, I guess. Before we head into more properties of logs. Let's see here. Yep. So a recap of our log properties. So we've got the inverse properties. We were just using these, right? We were using the fact that log base b of b to the x drops out and just leaves you with an x. We also used b to the log base b of x just drops out the x, right? So these are important. We also use this property a lot, right? Log base b of anything to the power of r, I'm allowed to bring that r down front or the power out front, and I can rewrite it as r times the log base b of a. And then last day we talked about the change of base formula, right? And for this reason, that's why we can use the log of any base if we're trying to get at this exponent, right? Because then if we need to simplify it even more, we can use the change of base formula. This one's new, this next box. New today. I was gonna say new, but that made me think like new mathematically. That's not true at all. Nothing's new in math. It's all old. Sum of logs. Notice that we have the same base, right? So we have the same base, b. But if I have the log of a plus the log of c, what I can do is I can combine those as one log by multiplying inside. That's kind of not super intuitive in the beginning, but it is super useful later on. And so addition outside, addition of two logs, and I'm not going to say with the same base, but of course they have to have the same base, makes multiplication inside the log. Makes multiplication Are they watching like a nature film or something? It does, right?
It sounds like an alien.
Tell us what you're watching. And share it to our screen. We want to know. So I will add and vice versa. There are scenarios where you've got multiplication inside the log, but you want to get at something inside the log. And so what you're going to do is you're going to rewrite it as the sum of two logs, right? And so moving in either direction here is really important. Of course, do we need this one? Not really. It's nice to have. Why don't we need this one? Let me show you. First, notice that you have log base b, base b, base b. They're all the same base, right? We don't really need this property stated. I'll give it to you, of course, but we don't really need it. Let me zip this up here. Because if we start with log base b of a minus the log base b of c, I can rewrite this as the log base b of a plus -1 times the log base b of c. Do you see it? Maybe. Knowing the exponent property, okay, this becomes log base b of a plus log base b of c to the -1. Uh-oh. I know what that looks like. So then now I have addition of logs of the same base, which means I can rewrite this as multiplication, which means I have log base b of a times c to the -1, but that is the same as a over c, right? Bring that -1 exponent downstairs, and I get log base b of a over c. Ta-da! You don't really need it, but it's nice. So what happens is if you've got division here inside the log, then you can break it up into the numerator subtracting or being subtracted by the denominator in terms of the logs. Okay. We have to add a lot of pages here for our work. And maybe what I'll do is I'll even add page here. We're going to write this single log as a combination of just in my head, I call them kind of unit logs. So that doesn't make sense. That's not a technical term. But we want to rewrite them, right, and expand this. So here, expand. So I have, I'll just start here. The log of 5x squared over y to the 4. So from that division property or the difference of logs property, let's start there and split up the numerator from the denominator. So that's going to look like this, the log of 5x squared minus the log base 10, of course, of y to the 4. There's lots of ways that we can solve these, right? What else could you have done? You could have simplified the exponents here right? 5x squared times y to the negative 4. We'd end up in the same place, so it doesn't really matter. So what's the next thing we're gonna do? I can split, I've got multiplication inside the logs here. So as long as I'm careful to add these logs and still subtract this log, then I'm okay. So I've got the log of 5 plus the log of x squared minus the log of y to the 4th. You can leave it there, or if we're expanding, then I want no powers inside the logs, or no exponents inside the logs. That's not obvious, so that's why I'm saying it. Okay. Which means that I can bring this 2 out front and this 4 out front, and then I'm left with the log of 5 plus 2 times the log of x minus 4 times the log of y. And now I'm done. There's no more expansion that I could do. So we're going to need to be able to move. Usually we try to simplify things and zip it up into a single log, but it is really useful to be able to move this way as well, right? Just using these log laws. Log laws. I'm going to erase this here. What if you have to rewrite this as a single log? So just one log base 10, nothing else. I'll give you 1 minute, a mad minute. Did you guys have to do mad minutes? Do you know what a mad minute is? Oh, it's like in grade school. You get 100, whatever you're working on, addition, subtraction, multiplication, division problems, and you have a minute to do them. It's a mad minute.
You just have to fill like the table, like 12 times 12, all the way up, and then fill out the tables.
Yeah, we had, these sheets of just random math problems. You have a minute to do it. It's a mad minute. Talk about math anxiety. I thought they were pretty fun, but yeah.
Only the final.
Pretty good.
Write your name down.
Or at least get, is it like Brian correct? At least get 30%. The date, so get it up.
That's nice for marking, I guess. Or pass it to the left. Have someone else mark it. Those are the days. What am I gonna do? I'm gonna bring these into the exponent, right? Because I can't use the addition property until I just have the log base 10 on its own, right? So that's why I need to bring these powers up top here. And I have plus log base 10 of y to the 3. But now I'm adding, I have to check, do I have the same base? Yes, I do, and I'm adding. And then I remember that I can zip that up one more step by multiplying inside the log. So the log of x squared y to the 3. Nice. Okay. All these properties, let me just write a note here. So all the log laws just because I think it's more fun to say log laws. Apply to logs of any base. Right, so that's good to remember. One thing, I'll do it in red. Note, if you have the log of a plus b, there's no expansion that you can do here, right? Even this does not simplify or expand, right? It's tempting to do the log of a plus the log of b, but that's not the property. We need multiplication inside in order for it to turn into addition outside, right? And so same thing with the log of a minus b, oops, yikes, a minus b. Ditto. Right, so if you have addition and subtraction inside, then there's nothing you can do. You're stuck. What if we have to solve something like this? And maybe I'll keep it on its own page here. And get creative here. And by creative, I mean add a page. There. So now we're ready to tackle something like this. So I want to solve for x. Solve for x is implied. Okay. Nothing to it but to do it. We want to get at the x inside the logs, but how can we do that? To get at something inside the log, we're going to need to take, this is base 10, so 10 to the power of the logs, but I need a single log to be able to do that, right? And so what we're going to do is we're going to write as a single log, as a single log. Why can I do that? Let's check. I've got log base 10, that's a good start. And I have subtraction of the two logs. And so by those log laws, I can rewrite this as okay. Because I'm going to be manipulating this side, what I'm going to do is I'm going to write 2 on the left-hand side, because then I can move it all the way over, and then I can manipulate the right-hand side and it can kind of change. All right, so I'm going to rewrite this as 2 is the log of x plus 5 minus the log of x. If I rewrite this, I get 2 is the log of x plus 5 divided by x. Right? Or what could you have done? You could have brought that -1 exponent upstairs, right, from here to here, and then you'd have addition of the logs, but then you'd have x plus 5 times x to the -1. It really doesn't make a difference, and so I'm just going to use the subtraction property. Okay. Now I've got a single log. All right, so I've isolated the log. The log is isolated. I've got everything inside the log, or moved everything else over to the, I guess, left-hand side in this case. So now I have log base 10 here is implied. So what I'm going to do is I'm going to take 10 to the power of both sides. All right, so this is log base 10, so I can rewrite as 10 to the power of 2 is equal to 10 to the log base 10 of x plus 5 over x. All that's in the power. I used log base 10 because of this first property, b to the log base b of x, so 10 to the log base 10 of whatever's in the inside the log just leaves you with x, right? And so that's the reason I use 10. And so this is going to essentially cancel. They go to 1, but so then I have 10 to the power of 2. You don't want to forget that you did it to the other side as well. I love to forget. Is x plus 5 over x. Now, if I'm trying to solve for x, what I'm going to need to do is I'm going to bring this x over to the left-hand side. I'm going to rewrite 10 to the power of 2 as 100. I think that's nicer. And so I get 100 times x is x plus 5. So then I can subtract x from both sides and I get 100x minus x is equal to 5. So I get 99x is 5. So x must be 5 over 99. I'm going to go ahead and guess that's not a nice number. It's not. So I'll just leave it. We need to check, right? I can't take the log of a negative number nor a 0, right? And so we need to check that we had here, we're taking the log of x and the log of x plus 5, right? But x plus 5 is always going to be bigger than x. And so if you kind of think about the domains of each of these, right? X plus 5 has to be greater than 0, but also x has to be greater than 0. And so I'm more concerned with this x here. So we're going to check that x is greater than 0 and 5 over 9 is greater than 0. 0.0505, let's say 1 is greater than 0. Check. And of course, 0.0505 plus 5 is also greater than 0. Okay. Nice. How about another one? I'll do it on its own page. Oh yeah. Let's see here. But this isn't the log of 2. So if it was the log of 2, it would work. But yeah. Nice. How about this one? This little guy looks like a troublemaker to me. Why? Because I'm going to kind of glance ahead and I see when I combine this as a log, I'm adding 2 logs, which means I'm gonna multiply x times x plus 3. So all of a sudden I have an x squared. Uh-oh. Why is that uh-oh? So then we need the quadratic formula. As soon as I see an x squared, how I'm going to solve it is using the quadratic formula. So let's buckle up. I've got the logs of the same base and I'm adding them together. And I think we're ready to just kind of go for it. The log of x times x plus 3 is equal to 1. So I get the log of x squared plus 3x is equal to 1. Now I have log base 10. So I'm going to take 10 to the power of both sides. But what's nice is the log's going to go away. X squared plus 3x is 10 to the 1. So now I'm left with x squared plus 3x is equal to 10. Because 10 to the 1 is just 10, so I'll write it simply. Now the quadratic formula, right? This looks like a quadratic. And it is. We need to use the quadratic formula. We need a squared plus b, oops, forgot the x's. A squared, oh gosh, nope. Nope, forget I said anything. Ax squared plus bx plus c is equal to 0. So if ax squared plus bx plus c is equal to 0, bump that down. Then how do I solve for x? X is negative b plus minus the square root of b squared minus 4ac over 2a. So the first thing I'm going to do is I'm going to move this 10 over to the left. And so then if I subtract 10 from both sides, I get 0 on the right-hand side, which matches what the format that I wanted in. Right? And so I have x squared plus 3x minus 10 is equal to 0, which means a is 1, b is 3, and c is negative 10. So I can use the quadratic formula and I can say that x is negative 3 plus minus 3 squared minus 4 times 1 times negative 10. Why am I glad when the c is negative? Usually that's how I'm going to get addition inside the square root. If I have subtraction, then it's likely I'm not going to have any solutions because I'm not allowed to take the square root of a negative number, right? Unless a is negative. Divided by 2 times 1. Okay. I have negative 3 plus minus, and I have 9 minus 4 times negative 10. I get 49. Divided by 2. The root of 49 is something nice. Phew. plus minus 7 divided by 2. We'll do the lower one first, just because of how they will appear on our graph, but it doesn't matter. -3 minus 7 divided by 2. So x is going to be -5 or -3 plus 7 divided by 2 or 2. This is where we need to be super careful, right? Because now we need to check the domain. The domain, I have just an x here, so that means that x has to be greater than 0. X greater than 0 and x plus 3 greater than 0. But x plus 3 greater than 0 just means that x has to be greater than -3, but it's overpowered by x has to be greater than 0. So these are the solutions to the quadratic, but the only solution to the log function is 2. Therefore, x equals 2 is the only solution. Whee! So many exclamation marks. I'll cut that one. Whee! Lots of things to keep track of. Any questions about that one? Just toss in some quadratic formulas in there. Rude. Uh-oh. Usually people don't like word problems. I'm one of those. I find they're difficult, but it is part of the fun, I guess. How about this one? I'll remind you what the formulas are for the continuous growth rate and the, I guess, annual growth rate, but then I'll give you some time to try it on your own. So let's see here. Where was it? It was last day. So we have, I'll just copy this. I'll zip it up a little bit so I can have it on the same page. Okay. Give you 3 minutes to try it. I'll pause this though. Let's hop back in. We have town A starting at 1,000 and it's growing at a continuous rate of 6% each year. Now I'm going to just underline all the town A information in blue, and then I'll underline all the town B information in orange. The population is currently 5,000, but it's dropping at an annual rate of 5% each year. Uh-oh. My voice needs to hang in there. And we want to find when will the two towns' populations be equal. So one is starting at 1,000 and it's growing, and the other one is starting at 5,000 but it's dropping. And so eventually they will meet at some point. Now, what you can do is if we use these functions as they are, right, then x would be the time, right? The number of years, because the rate is each year and each year. So x would be in years. Okay? Or you can write it as t, but because this is how we have the functions, right, then what do you prefer? Should I rewrite it as t or keep the x? I'm tempted to just keep the x, just because this is how we have it, but I'll make a note here. Note, in this question, x is equal to t in years. So if you wanted to, you could rewrite where you see an x, you could rewrite it as a t, but I'll just keep it as x. Okay. So we've got two different equations depending on if we've got a continuous growth rate or the annual growth rate. Okay, and so what I'm going to do is I'm going to do them kind of side by side. I'll say town A, and then I'll have town B. Town A has a continuous growth rate. What's the 1,000? That has to be your A, right? F of 0, so the starting point is A. And so here, F of 0 is A, which in this case is 1,000. Anything to the power of 0 makes 1, and so then you're just left with A in both scenarios. And same thing with town B. F of 0 is A, which is 5,000. So your starting point is always your A. Okie dokie. We've got a continuous growth rate, which means in general, my function is going to look like this: A times E to the K times X, where K is the continuous growth rate. We just said that A was 1,000. And it's growing at a continuous rate of 6% or 0.06. So I'm going to leave it at 0.06 because I don't have to make it decreasing. If it was decreasing, it would be negative, right? But 0.06 times x. And that is the population function. So we could use, instead of f, we could use a capital P usually for population sizes. And instead of x, we could use t. Right? I'll just write those briefly above here. Or P of t is 1,000 times e to the 0.06 to the x. I'm going to keep the blue version because it matches what you'll have on your formula sheet. How about town B? Oops, wrong color. Town B is currently at 5,000, but it's dropping at an annual rate of 5% each year. And so we're going to have f of x is a times 1 plus r to the x. So f of x is a times 1 plus r to the power of x. We said that a was 5,000 and it's dropping at a rate of 5% each year, which means the rate is negative 0.05. So R is negative 0.05. So plus negative 0.05. If you want to go straight to minus, that's fine too, to the power of x. We know from exponential functions, right, that if I have this little guy, which we were calling b, right, if b is between 0 and 1, then I have exponential decay, right, which makes sense. F of x is 5,000 times 0.95 to the power of x. So we can sketch the graph if you want. Maybe you don't want. When x is 0, it's going to be at 5,000, and it's going to be decaying at some point x, and town A is going to pass through at 1,000. And at some point here, right, at the intersection, that's where the populations will be the same, P or F of x, or the population at time t, or P of t if we let that axis be called t, right? Or P of t is 5,000 times 0.95 to the power of t. Either way, we have to set them equal to each other to find the point of intersection, right? What's nice is I have f of x and I have f of x, so I'm just going to force them to be the same and solve for the value of x that makes that happen. Okay. So town A brings its 1,000 and e to the 0.06, oops, 0.06x, and town B brings its 5,000 times 0.95 to the x. Okay. Couple of different ways we can solve this. It's kind of a choose your own adventure type of thing. I've got x's in the exponents that I want to try to solve for. Now, what you can do is you can simplify things a little bit by dividing both sides by 1,000. That might be nice. And then you don't have to lug around the 1,000 and the 5,000. So let's do that first. So divide by 1,000. Divide by 1,000. 5,000 divided by 1,000. I'm going to say gets me to 5. And so I have e to the 0.06x. I can't keep up with the two colors, but you see where they started from. Is 5 times 0.95 to the power of x. I've got two options for my base because at this point, I can't get rid of this 5, but I do have those log laws that I can use to separate these two out later. So I could use log base e, which is what I'm going to do. Or what could you do? You could use log base 0.95, just doesn't have the same ring to it. And so I use log base e. And so if we take the natural log of e to the 0.06x, and then I have to take the natural log of the other side as well, of 5 times 0.95 to the power of x. Okay. This, I use the natural log so it would cancel with the e. So on the left-hand side, I'm left with 0.06x. On the right-hand side, I'm not so lucky. There's no cancellation yet, or there is no cancellation, but I am multiplying inside 5 times 0.95 to the x. So I'm going to split this into 2 logs because the log of 5 or the natural log of 5 is just a number, right? It's a ugly number, but it is just a number. So I get the natural log of 5. I'm multiplying inside, which means I'm going to add the 2 logs on the outside of 0.95 to the x. But why did we do that? Because now, finally, I can bring this x down in front. I couldn't do that here, right? Because 5 didn't have a power of x. So if 5 also had a power of x, then I could do it, right? I could collect those exponents and I can bring them down front, but I'm not allowed to do that until I have just whatever is raised to the power of x alone. Now we're getting someplace. I've got 0.06x is the natural log of 5 plus x times the natural log of 0.95. As long as you convince yourself that the log of a number is just a number, right, then what can we do? If I'm trying to solve for x, I can subtract x log 0.95 from both sides. Let's do that. So then I have, it's a new page, so I'm just going to rewrite from the previous page, no change yet here, there. So now 0.06x minus x times the natural log of 0.95 is the natural log of 5. I did that so that I can pull out a common multiple of x on the left-hand side. So I get x times 0.06 minus the natural log of 0.95 is the natural log of 5. This is just a number. I want you to keep it like that though, for the exact answer. Because then what are you going to do? You're going to divide both sides by 0.06 minus the natural log of 0.95. And finally, we have x is the natural log of 5 divided by 0.06 minus the natural log of 0.95. Ta-da! We can use our calculator for an approximation. All right, let's do that. Natural log of 5 divided by, and I'm going to use brackets in the denominator, so it's all being divided. 0.06 minus the natural log of 0.95. I get x is roughly 14.46122986. What does that mean? That means that here, x is roughly 14.5. 14.46. Let's just say 14.5 years. So therefore, the populations, when will the populations be equal? The populations will be equal in 14.46 years. Therefore, the populations will be equal in approximately 14.46 years. How about this? Let's do a follow-up question. What will the population size be? If you still have that exact answer on your calculator, I would store it. So I'm going to store it. I'll store it in A. And I make a note to myself where I stored it so that I can remember later on, right? And we played around with the storing of the functions before. So that's good. If the populations are equal, it doesn't matter which one of these equations I use, right? Because as long as I put in x into either one of these, then I should get the same number, right? And so what we can do is, I'm going to copy this. And I'm going to,
I'm sorry.
Yeah.
So, why is the 1,000 times the
this one here.
yeah, one is not 1.06. It's
Oh, because here, so in this equation, K is the continuous growth rate,
oh,
right?
yeah.
And so the growth rate was 6%, and so K is going to be 0.06. Nice. Yeah, unlike here, right? Usually we do 1 plus R, but it's just the rate. So substitute what I stored in A for X. I'm going to try it with just 14.46 and see if there's a large difference. Let's see here. If I have, I'll do this side first. Store A times 0.06. E to the power of that, kind of reverse engineering it, times 1,000. I get a population size of 2,381.364855. And of course, if they're at the intersection, then the other one should be the same, but let's do 0.95 to the power of shift recall A times 5,000. Phew. 2381.364855. Therefore, the population size will be 2,380 roughly. I'll do a little squiggle in front because I can't have 0.36 of a population of a person. Let's see, versus using x equals 14.46, the rounded value. Do you expect the answers to be exactly the same? Not really, right? Because that would be the same as looking at the point well, in my fake diagram here, 14.46 is just to the left of the intersection. But I'm curious to know if there's going to be a kind of a visible difference on our calculator. So let's try it. 1000 e to the 0.06 times 14.46. Make sure you know where your E button is. E to the power of 0.06 times 14.46 times 1000. I get essentially 2381, 1891, 36. Versus 5000 times 0.95 to the power of 14.46. 95 to the power of 14.46 times 5000. Hey, I used blue for this guy. Just to show that they're not exactly the same. And you want to be careful with rounding, right? This one would round to 2381 and this one would round to 2382. Does it really matter? Not really, but just something to keep track of. So when you can, use your store function and use the exact value to get the exact same answer. Okay.
See, on the decimal, the one that is decimal.
Oh, on Desmos?
Yeah, on decimal is 14.6.
Really?
Yeah.
Let's see. That's weird. Okay, let me remember. 1000 times, and then the functions exp of 0.06x. So in Desmos, the exp is e to the power, and then whatever's in the power is inside the brackets. Oh, I was wondering why it wasn't showing up. Well, because we know it crosses at 1000.
Never mind. Actually, I just use my way.
Oh, but let's try it anyways. Let's see here. 5000 times 0.95. Oops, 0.95. 5 to the power of x. Uh-oh. Let me put a guide in here. How do I make a guide? I'm going to draw a line at x equals 14.46. Oh boy. I know I'm somewhere up in the 3000s, or sorry, 23,000s. 23, 20, 30, 35, 60. There, I saw something, a glimmer of hope. It's because I put the line at 14.46. And I can't see which one's which.
You have decimals. Great.
I know.
Yeah.
I wish I could actually. Because then I could ask you way harder questions. Yeah.
At the point where you divide it by 1,000.
Yeah.
Can we not multiply the 5,000 or the 5 by 0.95? Why do you?
It's because, where is it? Here.
Like when they were together, I wanted to multiply.
Here. It's
4.75.
It's because 0.95 is to the power of x, but 5 is not to the power of x.
Oh.
Yeah. If it was, then you could have pulled it out. But 5 is just 5. And then this is to the power of x. So that's why you can't do a little mashup there. Okay. And we don't have a clock, but time still exists. Nice. Time does, in fact, still exist. Let's see here. I think that's the end of that section. And I am going to be so cruel and just do the section on the graphs, but we're going to do a very, very mini version, right? What I'm expecting you to be able to do in terms of the graphs is just have an idea of what these things would look like, right? Be able to kind of sketch them out and kind of visualize this scenario. Right? This was 4.4 and we're just about to start 4.5. I don't know. 10 crucial minutes. No, we did most of 4.3 last day. And 4.2 was just itty bitty, again, on graphs of exponential functions. Okay, so I am saying that this is a mini version. So if you're reading the textbook, what? I know. It's a thing you can do. But then you can ignore a lot in section 4.5 because, like I said, I just want those core concepts, like can you sketch it out, like we did for exponential functions. The main thing that I need you to keep track of is that a logarithmic function looks something like this. And the domain of a log, right? The domain of any log of x, I'll do log base b, even though I had any. Anyways, kind of redundant. But the domain of any log is that x has to be greater than 0. Right? We're going to add that to our list of domain rules that we have, right? I can't divide by 0. I can't take the square root of a negative number, and I have to have a positive number, a positive non-zero number in a log, right? I'm trying to not say negative because it also includes 0. I can't take the log of 0. You can try it on your calculator, but it's not going to work. And so in terms of the graph, all those rules are reflected in the graph. And so if you have a function log base b of x, then you have a horizontal intercept at 1, 0. So when x is 1, y is 0. Okay. And so here, this, when x is 1, y is 0. The graph has a vertical asymptote at x equals 0. And so here, at x equals 0, and I wonder if I should have been drawing these down here, but anyways, whatever. So vertical asymptote at x equals 0. Meaning it'll approach x equals 0, right? And we're allowed to take values very close to 0 in the log, but we can't take it at 0. Now the graph is increasing. Increasing means that it's going up like this, but it's concave down. And so increasing and concave down, right? If you have to kind of see which way your bowl is facing, it's facing down. And so it's increasing, but concave down. And the domain of the function is x greater than 0. And the range of the function, it can take on, or it can yield values between negative infinity and positive infinity, right? And so on the y-axis, right, the output can be any number, any real number. I don't remember what I was going to put there. I think the graph that I drew up here, but oh well. So I'll just bump this up. If we have to find the domain, right, that is something that I need you to be able to do. Find the domain. We've already kind of relied on finding the domain, right, for identifying reasonable answers, right? And so we need to be able to find the domain. In this case, I first look out for division. There's no division. Then I look out for even roots. I don't have any even roots. Then I look for logs. Well, I do have a log. Surprise, surprise, surprise. Which means that here, 4 minus 3x has to be greater than 0. We can solve this with just the inequality, and that might be a good thing to practice. We can also use test points, right? If you set it equal to 0 and then figure out where on this line, because 4 minus 3x is just a line, right? Y equals mx plus b. I've just got an 1x. And so this is a line. In fact, it has a negative slope. And so I already know what this thing looks like. Y equals 4 minus 3x. We don't need to know what it looks like, right? We can just rely on the inequality, but it is helpful, right? If I let x be 0, then y is 4. Right? Then it's at 0, 4. And what else can I do? I can say, okay, here, if I let y be 0, 0 is 4 minus 3 times x. I have to solve for x to figure out what that value is. Or we can just use the inequality. And I'm going to avoid working with negatives and just add 3x to both sides. Right? Remember with the inequalities, if you if you multiply or divide by a negative, then you have to switch the sign, right? And so we get 4 is greater than 3x, which means that 4 divided by 3 must be greater than x. Okay. That is the domain, right? X is less than 4 over 3, which puts this point at 4 over 3, which you can check, right? Put in x equals 4 over 3 makes 4 over 3 times negative 3. The 3's cancel and I get 4 minus 4 is 0. And then from the graph, you can say, okay, well, x actually has to be less than 4 over 3. Or if you just want to use the inequality, if you don't like graphs, which is totally normal, no one likes graphs, especially me. I used to avoid them like the plague. I just, ugh. Like, I'll never get a handle on the graphs. But then I did, and it is very useful. So, but it took me many years. So I can't blame you if you don't like the graphs. Another thing that you could do is if you don't like graphs or inequalities, you can find out where 4 minus 3x is equal to 0. That's fine. Find where 4 minus 3x is equal to 0. And then use test points around that point to see where it's greater than 0. Then use test points to find where 4 minus 3x is greater than 0. Right? So what does that look like? Okay, I'm going to set it equal to 0. 4 minus 3x is equal to 0. Finally, something I like. It's going to look very similar, though. 4 is 3x, so x is 4 over 3. And I'm going to scoot this over. Dink. And I'm trying to remember. I feel like we've used, we used test points when we dealt with inequalities, right? Absolute value inequalities especially. And so we have used test points before. And so I've got 4 over 3 here. And then I just pick convenient values. So 4 over 3, let me just, 1.33. How about I do 1 and then I do 2? Just because this is roughly 1.33. So I need to pick a point on either side. I know I'm restricted because, nope, forget I said anything. It'll always work. No restrictions. So now if I plug in the test point, then I have 4 minus 3 times 1 is 4 minus 3, which is 1, which is greater than 0, I think. But if I do 4 minus 3 times 2, I get 4 minus 6, which is negative 2, which is not less than 0. Bad. I'll do a green check mark. Oops. Try to erase it. Which tells me that this is the interval that I want, not including 4 over 3, because that is where it equals 0, and I can't have it be equal to 0, but it can be any value less than that. So there, potentially 3 different ways of finding the domain and just kind of confirming it, right? You only need to use one, but depends on what you like. So therefore, the domain is going to be from negative infinity up to 4 over 3. Oops, 4 over 3, not including 4 over 3. I'll do a nice big bracket here. I know what you're thinking. Emily, you said we weren't gonna sketch any graphs like this. Let's use Desmos. And then we're gonna confirm these properties from Desmos. How about that? And I told you it's a mini version, then that's it for this section. So let's see if I can grab, if I can remember. And of course, I'm all zoomed out on Desmos. There should be a reset there. Okay, I want 4 times the log. Now the log, hey, I was doing the double screen thing, but not to you. There. 4 times, now the log is down in the function, so function's in the right-hand corner here. And you're gonna need to scroll down to the log. We'll just use log base 10 of 5 times x plus 2. We can figure out the domain of this thing, and that's a good thing to practice, right? 5 times x plus 2 has to be greater than 0. But once we graph this, oh, it's all flat because I'm so zoomed out. Hey. I'm gonna try to screenshot that with the points. Yes. Copy and delete feels risky, but I'm gonna try it. Save my camera roll. My virtual camera roll. Hey. Okay. So now it's still going to pass through 0, 4 because a is 4, right? Whatever's outside the log is your a. And so if I let x be 0, I get 4. The log of 5 times 2, 10 to the power of 1 is 10. Phew, it works. What did I check? Check. 4 times the log of 5 times 0 plus 2 is equal to 4. That's true. You can try it. But we get 5 times 2 is 10. 10 to the power of something is 10. 10 to the power of 1 is 10. And so 4 times 1 is 4. Whew. Okay. How about this little guy? What about when y is 0? Right. We can solve this. We can let f of x equal to 0 equal to 4 log of 5 times x plus 2. So now I can divide both sides by 4 and I still have just 0 divided by 4. And so 0 is the log of 5 times x plus 2. Log base 10 means I have 10 to the power of 0 is 10 to the log of 5 times x plus 2. As you get more comfortable, you don't need to write this step. As long as you write 10 to the power of 0 here, you're allowed to just drop down the 5 times x plus 2, because that was the goal of taking 10 to the power of something here. Gonna need a little bit more room. So these guys cancel. 10 to the power of 0 is 1, is 5 times x plus 2. So x must be 1 over 5 minus 2. 1 over 5 is x plus 2. So x must be 1 over 5 minus 2. Use your calculator. 1 over 5 is 0.2 minus 2. And you get negative 1.8. All right. The only thing that we don't really know is, okay, there's been a shift here, right? I suspect that this vertical asymptote is at where? Is at x equal to negative 2, just from x plus 2. And in fact, that's correct. So a transformed log function, we can rewrite it as a times log of x minus b plus k if it's being moved up or down, right? And if it's horizontally reflected, so like this, horizontally, yeah, around the x-axis, like I said, I'm not gonna, if I can't keep it straight, then I don't expect you to either. But then the negative is on the x inside, okay? But the key here is that x equals b is the vertical asymptote. Which is what we saw, right? X minus b, we had x plus 2. So then b must be negative 2. So here we have a vertical asymptote at x equal to negative 2. And those are all the things that I want you to keep track of. Okay. We're heading into a long weekend. And I said I would post a video. I'm going to, because we conveniently went into kind of a problem solving section, I am just going to post, you have them, but watch the videos for section 4.6, which is really just problem solving with exponents and logs. And it runs through all the different types of problems that we could have. And then problem solving with exponents and logs. And then I've got the notes, but there's no new concepts. Where is it? In 4.6, I just give you what's the half-life, and then find the half-life, those kinds of things. And so I'll post the solutions to these notes, and you can try them on your own. And we'll do some review, of course, next Thursday, but videos only for Tuesday. I won't see you until Thursday. I hope you have a wonderful long weekend. And with that, I release you.
I just